Newton's third law of motion tells us that forces always occur in pairs, and one object cannot exert a force on another without experiencing the same strength force in return. We sometimes refer to these force pairs as action-reaction pairs, where the force exerted is the action and the force experienced in return is the reaction. We can see Newton's third law at work by looking at how people move about. Consider a swimmer pushing off from the side of a pool as illustrated in the figure. She pushes against the pool wall with her feet and accelerates in the direction opposite to her push. The wall has thus exerted on the swimmer a force of equal magnitude but in the direction opposite that of her push. You might think that the two forces of equal magnitude but that act in opposite directions would cancel, but they do not because they act on different systems. When the swimmer exerts a force on the wall, she accelerates in the direction opposite to that of her push. This means that the net external force on her is in the direction opposite to the feet on the wall force. This opposition is the result of Newton's third law of motion, which dictates that the wall exerts a force on the swimmer that is equal in magnitude but that acts in the direction opposite to the force that the swimmer exerts on the wall. Forces are classified and given names based on their source, how they are transmitted, or their effects. In previous sections, we discussed the forces called push, weight, and friction. In this section, applying Newton's third law of motion will allow us to explore two more forces, the normal force and the tension. However, because we haven't yet discovered vectors in depth, we'll only consider one-dimensional situations in this chapter. The gravitational force, or weight, acts on an object at all times and everywhere on Earth. We know from Newton's second law that a net force produces an acceleration. So why is everything not in a constant state of freefall toward the center of Earth? The answer is the normal force. The normal force is the force that a surface applies to an object to support the weight of that object. It acts perpendicular to the surface upon which the object rests. If an object on a flat surface is not accelerating, the net external force is zero, and the normal force has the same magnitude as the weight of the system but acts in the opposite direction. In equation form, we write that N is equal to mg. Note that this equation is only true for a horizontal surface. The word tension comes from the Latin word meaning to stretch. Tension is the force along the length of a flexible connector, such as a string, rope, chain, or cable. Regardless of the type of connector attached to the object of interest, one must remember that the connector can only pull or exert tension in the direction parallel to its length. Tension is a pull that acts parallel to the connector and that acts in opposite directions at the two ends of the connector. Consider a person holding a mass on a rope, as shown in the figure. Tension in the rope must equal the weight of the supported mass, as we can prove by using Newton's second law. If the 5 kilogram mass in the figure is stationary, then its acceleration is zero. So the only external forces acting on the mass are its weight and the tension supplied by the rope. Summing the external forces to find the net force, we obtain net force is equal to T minus W equals 0, where T and W are the magnitudes of the tension and weight, respectively, and their signs indicate direction, with up being positive and down being negative. By substituting mg for net force and rearranging the equation, the tension equals the weight of the supported mass, just as you would expect T is equal to W is equal to mg. For a 5 kilogram mass, neglecting the mass of the rope, we see that T is equal to m times g, or 5 kilograms times 9.8 meters per second squared is equal to 49 newtons.